Hi and welcome to this video. Today we're exploring the Applied Maths Modelling project. So in this video we're going to explore the modelling project, which is worth 20% of the Leaving Cert Applied Maths examination. And we're going to focus on the sections of the report, so the introduction and research, the modelling process, interpretation of results, and the communication and innovation. And I suppose the goal and the aim for this video is really to understand each section, and I want you to be able to create a very high quality report and to maximize your marks. So before we start talking about the actual project itself, we need to understand a little bit more about that idea of modelling. So our applied maths course is broken into 4 sections. We have mathematical modelling with networks and graphs, mathematical modelling with the physical world, and mathematical modelling a changing world. So all of these, you can see by their descriptions, have mathematical modelling involved. So the idea is that this project will help us to link together all elements. Now, each project focuses on a section. It could be a specific real world topic. It could be a specific mathematical topic. It could be a mixture of both. So far, we are now in November 2024. We've had 3 mathematical modelling briefs. The first was on projectiles within a sport to maximise success. Last year's was looking at roller coaster motion, and this year we are asked to look at population changes. So in order to understand a little bit more, we need to take into account the weight of this modelling project. This is worth 20% of your overall grade. Keep that in mind, especially this year in 2024, where our due date has been moved from February to April. So this has meant that we have extra time, which is great, but you need to make sure that you still are putting in the focus into the 80% of your written examination. I know we can get lost in a project. We can spend a lot of time thinking about it and working on it and wanting to make it better, but you need to look at this in the context of your final grade. And this is only worth 20%. I say only worth 20%. That's really good to get a full 20%. However, think about the difference between getting a 90% and an 80% on that modelling project. If you get a 90 on your modelling project, you're going to get 18%. If you get an 80 in the modelling project, you're going to get 16%. So that extra 10% on the project is actually only worth 2% on your overall grade. And the reason I point this out is it can often be much easier for us to improve our grade in the written exam than in the modelling project. The time you put into improving your modelling project might be better placed in other places. So focusing on topics where you find that you might find a challenge, focusing on questions that are coming up each year, focusing on practice. I'm not saying the modelling project is not important. Of course it is. It is worth 20% and is worth doing well, but it's just really important to keep in mind the balance and not to allow your 6th year, so the second year of this applied maths course, to become all about the project and to forget about the other side. So I suppose in order to kind of really get to grips with our modelling project, it's important to understand why it's being brought in. So what we want to happen is we want to see a development of problem solving and critical thinking skills. We want to see you use mathematical modelling to address authentic problems, so something that's happening in the real world. We want to see you iterate solutions and refine models, and we'll talk more about this throughout the video. And we want you to present findings clearly and effectively. So this is what, at the end of the project, you should be able to look at and say, yeah, this has happened. I have gone deeper with my problem solving skills. I am thinking more critically about this particular topic, that you're using mathematical modeling in an authentic way. So in a way that makes sense. So mathematical modeling, we have this lovely diagram which is given in our specification, and we can see how we have a real world problem and how mathematical modeling helps us get towards mathematical models. And within that, there's going to be approximations and assumptions. So the first thing is to really understand this modeling cycle. So the first step of it is going to be researching our project, researching the problem. We want to understand what is the problem in the real world that effectively we want to translate into a mathematics problem. The second thing we want to do is define the variables and assumptions. So the one thing we need to keep in mind, and can be very difficult for applied math students, since students doing applied maths tend to be very good at maths and used to being correct. So when we research a problem in the real world and we want to move it towards maths, it's not going to be perfect. We try and improve it, and that's the idea of our iterations. But we often have to make these assumptions. And again, we're going to go through these in more detail throughout the video, but we need to simplify the problem. We need to make sure that the maths is not beyond us, because often to get perfect mathematics, we have to go way beyond the level that we are studying, and even the level that we're able to work with. So then we develop a model and we test it. And that's very, very important, because there's no point calculating a number and then not being able to tell if that number is good or not. So it's so important for us to be able to test our models, and usually we test it against real world values. So then when we're computing and analyzing our solutions, we're going to be looking at how do our answers compare to those in the real world. And when we look at our iterations, we want to go back and see, well, how do the solutions of our iterations compare to previous iterations? And then we're constantly refining it. Once we refine it, we go back to step 2 and we go again. So this is a cycle, which means we're moving around it. For us, I suppose the easiest way for me to explain the modeling cycle, and one that I use in class, is to use something at this point I hope all 6th-year students know, and that's the idea of our distance, speed, time, and the different iterations we could come to and that we could use to solve a problem. So let me present you with a problem. So I live 20 kilometers from school, and the problem is, well, how long does it take me to drive to school every day? So obviously this can be a very easy answer, in the sense that I could put that in Google Maps and Google Maps will tell me. But the idea of a modeling cycle is not to do research to get the answer. It's to do research to find out, what can I use? What information do I have to figure this out? Now, what is good about putting this in Google Maps or equivalent and getting an answer? It means every time I calculate an answer, I can see how close I am to the actual answer. And that is really, really important. If I don't have anything to compare it to, if I find out in iteration 1 that it takes me 3 hours, I have nothing I can say to say, well, that's ridiculous. Obviously, 3 hours to go 20 kilometers is ridiculous, but that's just my judgment on it. I need to be able to say it's ridiculous because actually the real answer is that it takes on average this amount of time. So if we were looking at this question, this is just to get a sense of the actual cycle itself, and in particular the idea of iterations. The first thing I might do is I'll start really, really simply and say, okay, let's look at just using our distance, speed, and time. So our DST triangle, you've learned this at Junior Cert Maths, you've learned this at Junior Cycle Science. And the main assumptions we have here is that the speed is constant. It doesn't change. So we have no acceleration, and that the car moves in a straight line for the entirety of the journey without any curves or bends. So this is what we consider like a linear motion, in the sense that if we were to try put curves, we bring in a bit of circular motion. So that's my iteration 1. And you might kind of scoff at that, especially as applied math students, say, oh, that's really too simple. But not necessarily. We can break this up and make this a very good first iteration if we really, really look at the assumptions here. So one of the things I've noticed as students work on this project is the assumptions tend to lack. we tend to keep them very obvious and we don't go deeper into it. So I'm going to give you a whole page of assumptions we can make for this iteration. Now, you don't have to make all of them, you don't have to include all of them, but I just want you to really get that sense of our assumptions. So the previous two were the really obvious ones, but further assumptions could be that we assume the speed varies due to speed limits. Now, you might be like, hang on, you just said the speed is constant. But we can actually break this problem up into little sections to make it more realistic. So I could say, right, well, on that 20-kilometer stretch, for some of them, I'm in a village. For the next part, I'm in country roads, which has a speed limit of 80 kilometers per hour. And then I move into a really good road where it's 100 kilometers an hour. Maybe I get on the motorway, so it's 120 kilometers per hour. So I can break these up into sections where I do deal with the speed limit. So I can make it more realistic rather than just saying I'm going the same speed for the absolute whole journey. So we can assume that there is no acceleration or deceleration, which means we assume we go from a speed to zero or from a speed to another speed without any acceleration or deceleration. Now, that in the real world is again kind of ridiculous. However, from a mathematical point of view, it is simplifying our problem enough that we can actually work with it. So we can take into account that we could have traffic lights, that we could say, okay, well, for the whole project, we're doing the same route. We're just refining our maths. So we could look and say, okay, I can see where the traffic lights are. On average, they're going to be red this much. On average, there'll be a stop of this length there. We can build all that in. Maybe it's congestion. We can look at taking into account that the traffic slows down at certain places, so like crossroads, intersections, or around schools, or so on. We can make an assumption about the weather and external forces. So we're going to external factors. So we can assume clear weather for simplicity, but we could say, but we know that there is the potential for delays in adverse weather. Maybe you want to work just with adverse weather. So we are making an assumption here. Every day is not the same, and we think of all the things that can affect the time it takes for us to travel in. So wind resistance is negligible. Again, maybe on a really, really bad day, we really should take that into account, but we're going to ignore it just to keep it simple. So then for our driving behavior, we can say the driver maintains a constant speed within zones, but adjusts near obstacles. And again, that adjustment is ignoring acceleration and deceleration. We're saying that, we're not taking into account delays on stops. So if, for example, we assume that the traffic lights are red, for 2 minutes, that is, we keep it 2 minutes, we're assuming there's very few delays as we work with stops. So then for precision, the journey distance of 20 kilometers reflects a practical driving path and is used as the basis for displacement calculations. And this may not be 100% accurate because we may not take into account the fact we're going around parked cars and so on. And then fuel efficiency and vehicle dynamics. So we're saying that actually we're able to go the same speed no matter what's happening. That means that there's no impact due to fuel levels or vehicle loads. So per passengers or cargo if I'm bringing somebody else. And then timing variation. So we're excluding factors like delays due to school drop-off queues or finding parking or things like that. So what I really want to demonstrate to you here is the idea of our assumptions, that we can really focus in our iteration about making it as accurate as we can while still making it as simple as possible. So I have taken something that's quite ridiculously simple, so assuming no acceleration, which is crazy. And you might say, okay, but could we just say, yeah, if I was traveling at this speed for the whole journey, then it'll take me this time? It's like, yes, but that's not a great iteration. It could be much better, even with the assumption of no acceleration, because we could take into account different sections. We can break it down. So even if you start with something very, very simple, don't be afraid on trying to make it more accurate. So just because it's simple in the first iteration doesn't mean you shouldn't strive to make it as accurate as it can be given its limitations. So then the second iteration would be moving to our equations from uniform acceleration, and the assumption being that the acceleration is constant or uniform throughout each section. So again, maybe using that same sections we talked about from iteration one. And again, the second assumption being that the car moves in a straight line for the entirety of the journey without any curves or bends because we don't want to bring in circular motion. But again, we can have a page of assumptions here that are very similar. So now we're saying that the speed is still varying due to speed limits, and now we're going to incorporate acceleration and deceleration phases. So we didn't have those before, okay? And they're uniform and consistent, which means you accelerate at the same, so it's a constant acceleration that we have. So we can see here in yellow, I'm bringing in some extra assumptions. Everything else we have already kind of talked about. Um, Everything else is still there from iteration one. So like if you were working in your project, in your modeling project, and you have assumptions that are consistent throughout, so they're used for every single iteration. Well, don't put them in every iteration. Why not put them at the start before your iterations, maybe even in the introduction section? We'll talk a bit more about sections in a minute. But you don't want to waste your word count. So your word count is 900 words. You don't want to waste it repeating yourself if it's not beneficial. Like a lot of this, like that's probably OTT on the number of assumptions that you need. But I'm just giving you an example that sometimes, when a student is working and you point out about what could be your assumptions, they're very limited in what they think about. So this is really just getting you to really think about the assumptions that could be there. So the last iteration, iteration three, and three is a good number. Like you're not limited to doing three, you could do more. Two probably could be okay if they're good enough. Three is a good safe number. So iteration three, we would look at using the idea of differential equations and calculus. So it's non-uniform acceleration. So the acceleration is not a constant. It is maybe a formula, it may be dependent on the velocity or so on, but the second assumption is the same. So for this whole piece, it's really, really important that we remember that we're not taking into account any curves. Now, if you want to do iteration four, you could start dealing with the idea of curves and bends. You could bring in a little bit of circular motion if you wanted to. But our focus here is looking at non-uniform acceleration. So thinking about how we get acceleration, which is dv dt, or the second derivative of displacement. Again, some further assumptions. So we can see here in yellow the extra assumptions, and I've actually had to take out some because there was just not enough space on the page. But we're following through a lot of the same assumptions as before, but we're saying acceleration, cruising, and deceleration are modeled using realistic functions. This is an acceleration phase, there's a cruising phase, there's a deceleration phase, and the acceleration changes are smooth with no sudden spikes or drops. The driver adapts their speed to match road conditions, but without abrupt changes. So we can really see how the assumptions are, well, first of all, staying the same from iteration to iteration, and secondly, how they then change. And the focus really should be on where they're changing. That's the big one for us. How are they changing and where are they changing? So I love this as an example for, giving students the idea of what we mean by iterations and how you can start and you should be starting very, very simply and building on that. And when you're doing your project, it's very common for students to maybe start at the end. You may work in a way that your brain just automatically gets um, the most accurate model, or it works with the most assumptions or the least assumptions, whichever way you want to think about it, but it ends up with what will eventually be your iteration three. So if you find your first iteration, the one you do first, is very complicated and it could be simplified, don't be afraid of simplifying it and doing that as iteration two. So the order you do this in, yes, we should start at the easy one and we should improve it and get to harder ones, but that's not always going to be the case. So don't be afraid of simplifying it. So let's actually work through just the sections of it. I'll give you some tips and we'll look at the marking and so on. So this has come from our marking scheme. So we can see that there are 4 sections. You have something like this, I think, in both your brief and your in and in your reporting booklet. And we can see that there are really 3 sections within the report. And then there's this last piece, the communication and innovation, that's not a distinct section of the report. So 20 marks are going for the introduction and research, 50 for the modeling project or the modeling process, 15 for the interpretation, and then this extra 15 that's not a distinct section. So let's work through this section by section. Let me give you some tips and just talk about how to work with each section. So the first section is introduction and research. It's 20 marks, and from our marking grid, they've told us that this is background research on your brief, identify specific problem or problems to be modeled, research the specific problem or problems, identify relevant variables, and present relevant data, provide citations and references. Okay, so what I would say is majority of students will be looking at a singular problem. You can bring in multiple problems, but it does become more complicated and you're splitting your time. So background research is the information that you're presenting that you found when you did your research. This can be presented in whatever way you want. Remember, we're very limited on word count, so bullet points are your best friends. Headings, that way to lay it out, brilliant. Don't be afraid to use pictures. You are limited to 20 images in your project, but sometimes an image that you find online shows something that would otherwise take you 100 words. So put that in. Just make sure that you reference it. Any information that you get must be referenced. Even if you're rewriting it, you must include a link if you got it from a website, or if you want to do a full citation properly, that is absolutely fine. There are no specifics on how you're meant to reference your project. So if you reference it in a certain way in other subjects, that's absolutely fine. My advice on it would be within this section to have a piece at the end where all your references go, because they do not have to be included in your word count. So if they're at the end of the section, it's easier to exclude them. If they're within the text, it's a little bit harder to do. So, the specific problem, identifying it and researching it, that is probably, in my mind, the most important thing you have to do. Because if you pick a problem that is, maybe hasn't got a lot of information around it, it it ruins your whole project. It means a bad question. I say bad, but as in a poorly chosen problem can lead to a poor project. Now, that doesn't mean a really good problem leads to a really good project. Obviously, you need to put a lot of work into it. However, you do not want to limit yourself. So make sure you spend a significant amount of time on this research. My advice, get a Word document or Google Doc or equivalent. And when you're doing your research, just throw in those links. Because I promise a month down the line, you'll say, I saw something and, it was great. And now I don't know where it is. So don't delete anything. Even if you change your problem or you move away from it, just record everything you find. And like I said, maybe just even a link of it. So your research, what you want to do with your research is present any relevant information. You only want to include in this project what's absolutely relevant. Because again, 900 words, that's not a lot. So your variables, they're going to be probably something you do at the end of your project. What have you used? Absolutely make a list of what you think they will be at the start, but this needs to be reviewed and updated at the end because depending on where your project goes and what maths you do, that could change. Best way to give your variables are in a table. Explain what the variable is, what letter you use, what unit, and what value you're using for it if you have, or maybe values or different values you're using. It depends on what the variable is. Present that data in a very, very clear and nice way so it's easy to see. Um, when someone's correcting your work, you want to make sure that all this stuff is jumping out at them. I would advise again, headings, bullet points, don't make them search through paragraphs of words to find this information. And then citations and references at the end. So this is a more detailed marking rubrics. So we have 4 sections, very thorough, basic, and very basic. So focusing on that very thorough, the problem and variables are identified, research is presented and cited, data presented where relevant. So that's what you're aiming to do. Now that's a very easy section to do and do well. And some of the top things I'd say to you is ensure you have real world data to compare your answer with. Sometimes students choose a problem that's super interesting. However, it's so kind of interesting and a little bit out there that they don't have the real world data to then use for the rest of the project, which then limits how well they can do. So try and pick something that you know you have an answer to. If you want to model, so go back to the question we did earlier in the video. How long does it take me to get to work if I live 20 kilometers away? I have the answer. I know what my answer should be. So any model that I come up with, any model that I make, any calculations that I do, I know how far off I am or how close I am because I know the answer. So keep that in mind. You really do want to know your answer. And this is where we really need to wrap our heads around what the process or what the point of modeling is. It's not necessarily to get an answer because often we can Google and get an answer. What we're trying to do is develop a tool that will allow us to calculate that answer. So we want to find a way where if we didn't know the answer, we could get the answer, but we tested by using data that we do know. Okay, so keep that in mind. Use headings, bullet points, and or tables to clearly show your variables and data. I would say headings, bullet points, they're your best friends. Tables are so easy to do without having to do a lot of words. And put your references at the end of this section. Again, you don't have to. That is just a tip for me. I think it will be easier to keep that out of your word count then. It is easier to collect your information. You can add in things maybe that you found along the way that maybe just didn't end up being something specific in that section, but it helped to kind of color the whole project. So you can add in all of your links. If you used any books, if you used any journals, they can all be referenced in there. Again, a little heading saying references and all of those underneath. So the second section in the modelling project is the modelling process, and this is the biggest section. It is worth 50 marks, and it says explain and justify your model and assumptions, compute your solutions, present solutions using appropriate mathematical and graphical representations, and the analysis of solution or solutions, sensitivity to change in assumptions, comparison with the other solutions or real world data, and the iterative process. Now, when this is marked, it's broken into 3 sections. So I'm going to just work through each section and talk a little bit more about these points then. So the first section is section 2A, which is the modelling process, explain and justify, and that's worth 15 marks. Again, let's focus on this very thorough part. The model fully explained, including further iterations, assumptions identified and justified. The second section, 2B, the modelling process, compute and iterate. This is again focusing on that very thorough, the computation of mathematical solution or solutions, fully explained, and the full iterative process. And then 2C, again focusing on that very thorough for the modeling process, present and analyze. The solutions are presented using appropriate mathematical graphical representations. Solutions analyzed with reference to models' assumptions and other solutions or real world data. So really focusing in on that very thorough section, and we want to try and get as many marks as possible in all of those sections. So the first section here, the 2A, the modeling process, explain and justify. So we want to explain our model. We want to look at and we want to explain the further iterations. We want to make sure we have our assumptions identified and justified. So some top tips. Again, use your headings. Bullet points to clearly outline your assumptions. We talked a lot about assumptions earlier in this video. Where you have assumptions that are for all iterations, you can state those at the start of this section. You can even include them in section 1. Then for each iteration, you can update your assumptions. No need to use sentences. Bullet points are fine. Maths where possible to limit, so you're not using your word count. Only explain where necessary and no need to explain in each iteration. So often you can over explain. So obviously it does state that your assumptions are identified and justified. So if you assume something, you have to justify why you do it. However, only explain in cases where that is necessary. Do you need to explain why you did this? And if the answer is, oh, I did it to simplify, you're like, But now, why we say, justified. If you decide I'm going to assume my velocity is 20, why? Why did you pull that? Where did that come from? Did it come from your research? So in that kind of case, that's something where you could have that maybe as part of your variables table in the research section, and you can include it here, but just be careful not to start over explaining. Again, we're very, very short on word count, so that's why I'm saying it. If we had thousands of words, I'd say yes, explain away, better to over explain. But for us with our word count, we have to be very, very careful. And don't repeat things in each iteration. So what I mean by that is if you have explained why you've decided to use your velocity as 10 meters per second and you use it again, don't need to justify it again. Justify it once. Sometimes students feel like they're working through this project and they're writing it as they go. What I would say is the write-up tends to come more towards the end, because you'll start to see when you've your iterations finished what's common across all of them, what you can move to maybe above all the iterations, maybe do them at the start of the modeling process section, or maybe move them into the research section. So really keep in mind how to write this efficiently. So in each iteration, focus on the change of assumptions and explain briefly what you plan to do in the iteration. So I would, again, headings, iteration 1, here's what I'm going to do, here are my assumptions, then jump into your maths, okay? Keep it lovely and simple and straightforward. So 2B then is the modeling process, compute and iterate. So computation of mathematical solution or solutions, fully explained, and the full iterative process. So what we're talking about here is really showing your iterations. And by iterations, I don't mean just going, I have iteration 1, 2, 3 and doing whatever you want. We need to see that there is clear progress. We need to see that you have improved. So again, go back to the example I did earlier in the video. Look at how, we moved from having no acceleration to constant acceleration to non-uniform acceleration. That's a very clear iterative process. We are improving in each section. Okay, that's what it means. Why I'm saying label your iterations clearly is often if there's a lot of pictures and there's lots going on, it's hard to see where one starts and the other one ends. So just from a layout point of view, it can be very helpful. So link your iterations together, show your progress. So as you finish one iteration, you do want to connect it to the next. So for example, go back to our question we were doing earlier in the video. So I work through my first iteration and I find that it's going to take me 40 minutes to travel to school. And I look at that and I compare that to my previous, research that told me it should really only take me 30 minutes. And I'd say, okay, well, this is my answer. And I'm a little bit off because it should be 30 minutes. I'm getting 40 minutes. And one of the reasons I think this is the case is because of my assumption that there's no acceleration. So in my next iteration, I'm going to bring in acceleration. So then I move into my second iterations. This is what I mean by link your iteration together, really connect them, show how you logically move from one iteration to the other, show how they are connected, and show how you're making progress. Explain what your maths is doing. So this is what it says, computation of mathematical solution or solutions fully explained. So explain what your maths is doing and why, if relevant. Don't explain stuff you don't need to explain. But often, we want to understand what are you doing and why are you doing it. So when you're doing your maths and you're going to put in maybe a picture of your maths, or maybe you're going to type in that maths, just very briefly explain either before it or after it what is happening. Just give a very quick overview. It doesn't have to be long. Just say, I've worked this out, or here I've broken into sections. Explain what you're doing. So the last section within the modeling process is 2C, and it's present and analyze. So solutions presented with appropriate mathematical graphical representation, solutions analyzed with reference to models assumptions, or other solutions or real world data. So kind of links back to what I was saying in the last one, in the sense that we do want to connect those iterations. You want to compare each answer to the real world answer. If you do iteration 2, compare back to iteration 1 and your real world answer. Use tables and graphs to show results. It does say here, solutions presented using appropriate mathematical graphical representations. I will be saying to you, you should have at least one graph in there somewhere. Think about how to present your data. Maybe you wait until the end and present all solutions on one graph, but really think about how you're presenting it and analyzing them. So what you want to do is a mini conclusion for each iteration. You want to compare your answer back to the real world, previous iterations. It's okay if iteration 3 is worse than iteration 2. That happens, and that is fine. Just comment on it, work through a conclusion, compare it, hypothesize maybe why that's the case. Don't be like, I'm wrong, I need to fix something. It's like, well, yes, clearly something is wrong, but that's the whole point of the modeling process. We want to find the closest answer you can have. Now, you shouldn't have three iterations that are very, very far off your final answer. So if I did my 3 iterations and I was getting one was 2 hours, one was 4 hours, and one was 3 hours for a 30-minute journey, I clearly have some bigger issue with my project. However, if I'm getting 40 minutes and then I'm getting 35 minutes and then I get 20 minutes, none of those are 30 minutes, but that's okay. I'm getting closer. Sometimes I'm moving a little bit further away. I can talk about why that's the case. I can focus on my assumptions that might be doing this, might be leading to this. What else may I have? What else could I possibly do to help improve it? So many conclusions here. Okay, so big one, tables and graphs. I would be including at least one graph in the project, and then the mini conclusions. And then the last physical section of the modeling project is the interpretation of results. So here we're asked to get the interpretation of solutions in real world context, and it's your conclusion and reflection. The bigger breakdown gives us, if we want to get very thorough in this section, excellent interpretation of results in a real world context. So you want to compare your answer back to the real world. Now, you've already done that throughout your project. We just talked about it. However, what you want to do is figure out, well, which iteration is the most correct? Why is the most correct? What assumptions does it have that makes it more correct? Compare that to the real world and conclude on it. What we want to focus on is maybe how, if our answer is very different to our real world answer, what more could we do? As in, what would be our next steps if we were to continue? What would be, okay, I would love to have assumed something else, but maybe I didn't have the maths for it. But you can see progress in the 3 iterations. And now I'm saying, well, here's where the next step would go. So make sure that this is very much about your project. This interpretation of results section should be a very mathematical piece as well. It shouldn't be a one where you talk about, oh, if I could do something again, I'd start my project earlier. It's like, that's great, but that's not what this section is about. The conclusions are all about the maths. So there's no need to summarize all your results. Focus on the most accurate answer. We're talking about which one is closest to the real world data. Conclude why it's the most accurate. Focus on your assumptions. Compare it to the real world answer, and what could have been another iteration or next step to find an even more accurate answer. Okay, so you want to focus in on those. Think about the breakdown of your marks, but also what needs to go into each section in order to focus on kind of the word count you have for each of these. Realistically, for the interpretation, you shouldn't need to have huge word count in there. And this is a great place to add in more graphs, more tables, to kind of show the results, to put this forward in a much quicker, easier way to understand. So the last section within the marking is the communication and innovation, and it's worth 15 marks, but they're very clear that this is not a distinct section of the report. So this is one that really depends on your project. And the marks go for innovative and creative approaches and overall coherence. So again, let's focus on this very thorough. So to get 12 to 15 marks, project approach and or presented in a highly innovative and or creative way. Okay, I really want to talk about that because often students read this and think, oh, I have to come up with an amazing project that's really different and really out there. And in some sense, yes. However, like I mentioned at the start of the video, if you choose something, a topic that is so far off kind of what's the norm, you may not have real world data to back that up. And in that case, you're going to limit yourself on the whole project. I want to point out that it says the project is approached and presented in a highly innovative or creative way. So what I would suggest, pick a very straightforward topic rather than a really out there one, and think about how you could do something different in your approach. So don't focus on getting, something completely out there. So let's go back to the 2023 brief where students were asked to use projectiles to model something in sport to help I can't get the exact wording, but it was all about success in a sport. So if you pick football, as in soccer, there's a lot of information out there that you can work with. If you pick a very obscure sport, I can't even think what might be a very obscure sport. Maybe I don't know. Pick what seems on the surface be a very interesting but obscure. Let's say lacrosse. Okay, so it's not one that's played in a lot of places. It's not one that maybe has a lot of data, and you decide to use that. It's very interesting in that respect, but you may have limited yourself because you cannot get data from the real world about it. So it would be much better to do something related to soccer, a very common on the surface, a very common project idea, and do something different with it. Okay. So when we talk about innovation, it's not about coming up with like a mad topic. Keep your topic very much something straightforward that there's a lot of data for, and then approach it. So we're talking about your maths here. We're talking about the iterations that you choose. That's what we're looking for innovation in. Excellent overall coherence means that it reads well and there's no major issues. So keep your word count close to 900 words. You fill out the table. Don't lie. Don't lie. It's very obvious if a student has a much longer paper or a much longer project. So do be honest about your word count, and keep it very close to 900. Okay, it is a skill in itself, writing efficiently. Maximum 20 images. Do keep this in mind, because if you want to do a lot of graphing, or if you want to put in a lot of graphs in your project, if you want to put in a lot of tables, well, tables aren't as, I suppose, graphs, tables, pictures. So just be very clear about the images, that it's a maximum of 20. This impacts you if you decide to put in your maths using photographs. Okay, if you type in your maths, it's going to be different. Make sure any images are labeled. That includes tables and graphs. Make sure the basics. Make sure your graphs are labeled. Make sure they have the axes labeled. Make sure they have headings. Make sure they have scales. Make sure they have units. All the basics. Everything should be really, really put together here. Check your formatting and ensure pictures are clear. So last 2 years we've had like a box to copy into within our Word document, which is really tricky. But actually this year it seems to be gone, which is excellent news. Should make it easier for pulling in information and copying it into the file. Do make sure though that everything is within the margins that are specified, that is given in, I think, both the brief and the booklet that you complete. Ensure pictures are clear, and take more photos of smaller areas than high big photos, because it can be really, really hard to see. Make sure there's not a shine on it. There are some apps out there that allows you to take a picture as a document rather than a photo. They're very clear. It's like a scanning app effectively. If you can scan in your pages, that can make all the difference. And just from the overall coherence, what a really good tip is, maybe get someone to read your project to see do they understand it. And by someone, I mean maybe somebody who's maybe not mathematical, and maybe somebody at home will take a look through it and see do they get the gist of what's going on. Because if they're going, I couldn't even follow this, then we're in trouble. And they don't need to go through your maths, they just need to read the rest of the project and just see can they. And if they're like, oh yeah, I'm kind of getting what's going on there, that's a really good sign. So that section here, just be very, I suppose, just be very mindful of, little typos. Double check. Like Word has a tool to check your spelling. It might highlight things about grammar. Read through it. Spend time at the end making sure that all this stuff is in line, because that's a nice 15 marks that you can get quite easily if you put a little bit of effort into that. I suppose the innovation can be tough. I wouldn't focus hugely on it. It's one area that if you were brought down a mark or two because it wasn't hugely innovative, that's fine. You can really pull your marks up in other places. So this is just kind of roughly where I think your word count should be. I think the majority of the word count is probably going to be in your introduction and research. I say that because I think there is a lot you can put in there. I would say working with your variables, maybe doing an explanation of what your iterations would be. You can include in there your assumptions that are constant throughout each iteration, and that then saves word count within the modeling process. If you want to include all that in the modeling process section, then maybe move that word count around a little bit. The interpretation of results, about 200 words. So there again, just estimates. You might find that you need a lot more in one section compared to the other, but this will just give you an overview. Remember, references and the calculations are not counted as part of your overall word count. And if you're typing in your calculations, you need to bear that in mind, that the word count that you're given at the bottom of the Word document may not be correct. So it's not about counting each word individually, but you can count them piece by piece or section by section, leaving out your calculations. If your calculations are in a picture, it's a little bit easier. Okay, so just finally some project tips. So start early and manage your deadlines. Make a plan and make sure you're very clear on where you need to be at each date. Don't leave it all until the last minute and build in time to review and edit at the end. So many students, I speak from experience, work right until the deadline and do not leave themselves time to review and edit. And that leads to marks being lost in that last section because they haven't read through it, they haven't proofread it, they haven't simplified down some of the sentences to save on word count. So, really, do you try for yourself to have it ready a few days before your due date. That way you can really put in time to review and edit. And you do need to step away for a little while and come back to it really to see and to make sure you're not like skimming it. Like really put some time and effort into that. Research to ensure a question that will allow you to complete a good project. Don't underestimate that research section. So many students, again, from experience, I see they jump in so quickly and just want to do the maths. And yes, it is a maths modeling project, but if you don't have a good starting point, you won't be able to go anywhere with it. And I have seen students have to change their whole project maybe a month in because they made bad decisions at the start. So really, really focus on getting a very good question there. Focus on the things we talked about. Make sure there is enough data available. Make sure there is a real world answer that you can compare it back to. Have a think about what your iterations will be. So focus on clear and logical explanations. Try not to have them too wordy. Make sure that you're saving on word count where you can. Question if it even needs to be a full sentence. Okay, it's a mathematical modeling project. We are very, very content with seeing bullet points, with seeing, V equals rather than velocity is, so use that to your advantage. So don't over explain or add information that is not directly related to the project. Just don't. You don't have the word count for it. You don't like this is not a project to explain. So again, let's take the 2023 brief and I'm going to do my project on soccer. It's not for me in my project to explain what soccer is and what year it started and its history. That is not relevant. Okay? Um if I want to talk about my project and penalty shots. Okay, explain what a penalty shot is because the person correcting your project may not have any sporting knowledge and may not know what penalties are. So explain that. That's directly relevant. But soccer in general, does it matter when it started? Does it matter who the best team is, who the best player is? Like, really think, does this information actually add any value to my project? Is this needed? Would someone still understand what's going on if I took it out? So do you use technology? So spreadsheets, so Excel or Google Sheets are great to help you with any kind of data collection. It helps you with graphing. If you're trying to do something, um, if you're trying to do a calculation that's pretty tough and you kind of need to use a trial and error method, not great. However, spreadsheets can help you do that. So bear those in mind. Don't be afraid of technology. And the most simple rule, just do what you're asked. So follow all the instructions in your brief and your booklet. That means if they tell you to use a certain font, use it. If they tell you to use certain size for headings, use it. If they say fill in underneath the headings, do that. Okay, so follow the instructions. 900 words and 20 images. So all I have to say then is good luck on your project. Bear in mind when you're doing this that you are working on 20% of your grade. Make sure it's only taking up that length of time. Make sure you're not spending too long on your project. But at the same time, make sure that you give it a very good go. It's very reassuring to walk in to your exam knowing that you have that amount. So best of luck.